And so, when we're talking about the vapor pressure or the saturation pressure, that's the pressure in which the pressure of the liquid phase is equal to the pressure of the vapor phase. Okay? Alright, and we also know that at the saturation pressure, or if the system is at the saturation pressure, the delta G, which is the G of the vapor phase minus the G of the liquid phase, that is going to be equal to 0. Okay? Alright, and so if we want to figure out what the saturation pressure is of a system at a particular temperature, we need to identify, the conditions in which the delta G between the vapor and the liquid phases is equal to 0. Okay? All right, and so to do that, we need a equation for delta G. And so what we know is that the fundamental G equation is this. Where the negative s is just the partial derivative dg dt at constant v, and the molar volume here is partial derivative dg dp at constant t. Okay. All right. And when we're identifying the saturation pressure, we're going to do this at an isotherm. So we're going to do this at a constant temperature. And so if we're doing it at an isotherm, that means that our dt term is equal to 0. So this term is going to go away. Right? And so when we're calculating delta G for the isotherm, really all we care about is this part. Okay? And so what one could do, so similar to the strategy that we've employed before, is to figure out delta G, what we could do is just integrate whatever's left of the fundamental equation. All right, so we'd be integrating, just in general, from some P1 to P2. And if we tried plugging in the partial derivative there, we would have an equation that looks like this. Okay. All right. So at least, this, based on the calculus of thermodynamics we've used before, this seems like it would be a path in order to get delta G. But at least this approach is, in practice, a bit hard to do. And that's because, in general, this delta G, this dg dp term here is hard to calculate. And that's because, first of all, you're taking the derivative of the molar energy with respect to pressure, right? But the pressure function itself, like we saw when we talked about the different equations of states, it's a non-monotonic. Right? As in, for a given molar volume value at a certain temperature, you could actually or for a given pressure, you could actually have that pressure could correspond to different molar volumes, right? And so in any case, the pressure function here is kind of difficult to think about. And so just calculating dg dp is something that's very tricky. And so rather than just taking the calculus of thermodynamics approach that we've done before, in order to integrate this function, what we could do instead is we could just do something that you learned about in your beginning calculus classes. Okay, and so instead of thinking about partial derivatives, what we could do instead is we could figure out v dp by just using integration by parts. Okay. And so if you remember from calculus, if you're trying to integrate a v dp, that's the same thing as saying that you have PV evaluated at some P1, V1, P2, V2, okay, minus P dV at V1, V2. Okay? All right, and so if we fully evaluate this term here, what we have is V2, P2 minus V1, P1 minus the integral of from V1 to V2 P dV. Okay. And what I want to say again is that all the pressures that we have in this equation, these are all functions of the molar volume. Okay. And just to make sure we're on the same page, I'm writing, pressure 1, volume 1, pressure 2, volume 2 here, because this delta G equation is general. I'm not necessarily talking about liquids or vapors at this moment. I'm just saying this is just what the delta G equation would be. Okay? But for the case where we are talking about liquids and vapors in equilibrium, what we would then have is that our pressure of the liquid phase is equal to the pressure of the vapor phase is equal to that saturation pressure, and our delta G, which is equal to VV Psat minus VL Psat minus the integral of from VL to VV at the pressure function dV. If the liquid and vapor are in equilibrium, then that delta G would be equal to 0. Okay? And so not only do the pressures have to be equal, but that delta G needs to be 0. Those are both necessary conditions. Just having one or the other is not sufficient.